Let's jump right into this explainer. Today, we're looking at a fascinating, almost cinematic way to make sense of our incredibly complex global supply chains. And we're going to do it through a lens you probably haven't thought about since high school, physics class. I know it sounds a little unconventional, but stick with me because the connections here are absolutely brilliant.
So, to kick things off, I want you to think about this. What in the world does a basic electrical equation, something engineers use literally every single day, have in common with the intensely complex geopolitical tensions happening right now in the Strait of Hormuz? Like, how can a math formula perfectly describe the physical movement of massive cargo ships navigating international waters? Well, it's actually a pretty wild narrative.
Moving right into Section 1, the physics of global trade.
Okay, so before we get to the oceans, we've got to nail down this one fundamental rule of electricity. V equals I times R. Good old Ohm's law. It's the absolute bedrock of electrical circuits dictating exactly how energy flows through a closed system. And here's the secret. Once you grasp this little relationship, you are basically halfway to understanding the entire global economy. Let's quickly break down those letters. In a literal electrical sense, voltage, the V, is the driving force. It's what pushes the energy forward. Current, the I, is the actual flow of that electric charge moving through the wire. And resistance, the R, well, that's exactly what it sounds like. It's anything that pushes back, slows things down, or just gets in the way. So voltage pushes, current flows, and resistance pushes back. Section 2, Mapping the Geopolitical Analogy.
Now, before we really draw these parallels, I do want to make it super clear that we're using this as a didactic tool. It's an educational analogy to help simplify massive international systems, not some literal political commentary. Ohm's law describes circuits, sure, but it gives us this beautifully structured framework to see how global systems naturally react to pressure.
So, let's map it out. In our giant global circuit, the voltage represents the massive, unrelenting worldwide demand for energy and trade. Just like a battery provides the voltage to push electricity, humanity's huge demand for oil, consumer goods, and raw materials acts as the primary driving force pushing international commerce forward.
Next up is the current. In our geopolitical circuit, this current becomes the physical, continuous movement of thousands of oil tankers and cargo ships. These ships are traversing maritime corridors every single day to bring fuel to your local gas station and drop packages at your front door. It's the actual tangible flow of goods, all driven by that global voltage we just talked about.
And that brings us to the final piece of the puzzle, resistance. In our world, resistance becomes literally anything that makes shipping harder. We're not talking about a tiny resistor on a green circuit board. We're talking about political conflict, rigorous cargo inspections, or sudden spikes in insurance costs because a region got unstable. Basically, any geopolitical obstacle is resistance. Let's jump to Section 3, Case Study, the Strait of Hormuz.
We can see how this builds if we look neutrally at real-world events, like the tensions involving the United States and Iran around the Strait of Hormuz. When state actors clash, uncertainty naturally spikes. The market instantly responds with huge supply concerns. Effectively, this injects a massive, sudden dose of resistance straight into our global trade circuit.
And what's the result of that resistance? Well, analysts point straight to higher oil prices and severe concerns about supply chain disruptions. When shipping lanes become dangerous or honestly even just legally and politically complicated, moving that cargo instantly becomes vastly more expensive and a whole lot slower. The resistance directly impedes our current.
Which brings us to Section 4, the mathematics of resistance.
Let's just plug some numbers in here to see how this actually works. Imagine a perfectly stable electrical circuit on a workbench. Step 1, you've got 12 volts of power pushing. Step 2, you have an expected 4 ohms of resistance pushing back. Since 12 divided by 4 is 3, Step 3 shows everything flowing along smoothly at exactly 3 amps. That is a happy, healthy system.
But now, let's apply that exact math to our shipping analogy. Global demand, our voltage, is staying high. The world always needs energy, right? But suddenly, the shipping difficulty, our resistance, spikes dramatically because of those regional tensions. Since V equals I times R, if resistance shoots up and we still want the current to stay exactly the same, the system is going to require way more driving force, way more effort to push that exact same cargo through.
And what does that extra effort look like off the whiteboard and out in the ocean? Well, it's not a battery working harder, that's for sure. It translates directly into enormous real-world economic burdens. We're talking companies paying skyrocketing shipping and insurance premiums, ships being forced to navigate much longer, inefficient alternative routes, or even nations having to hoard larger, incredibly expensive inventories just in case.
Which leads us to a pretty stark reality. The cold mathematical truth of this equation is that if you don't, or literally can't, increase that driving force when faced with new obstacles, the entire flow of global trade is naturally going to decelerate. If you can't throw more money or effort at the problem, the current drops, the goods don't arrive, and the global economy slows down.
Finally, Section 5, Systems Under Pressure.
Physics explains circuits, sure, but analogies like this? They help us understand the whole world. Whether you're an electrician wiring up a new house or a logistics analyst sweating over international supply chains, Ohm's law perfectly demonstrates how interconnected systems naturally respond to pressure and obstacles. The relationship between the push, the flow, and the pushback, it's completely universal.
So, I want to leave you with a crucial thought to chew on. As our global circuit grows more interconnected, faster, and infinitely more complex every single year, where will the next surge of resistance come from? Which waterway or political event is going to be the next resistor to really test our system? Next time you see a supply chain break on the news, try mapping it back to V equals I times R. You'll be absolutely amazed at how clearly you can see the forces at play.